Garrison-Kimmel on small-scale problems with baryonic physics, fire simulations.
Thank you. Yeah, so great to be here again. Always a good time being in Santa Cruz at this conference. So I want to talk today about some work that's been about 3 years in the making. I think every year I've come here for the past 3 years, over here, I've talked about how I wanted to talk about this, so I can finally talk about this now. The runs are finally done, and we finally have some first results. So I'm going to dive in by talking about the missing satellites problem, which everybody in this room knows, so I'm going to go through it pretty quickly. Basic gist is if you look at a gravity-only simulation, you see thousands of subhalos, right? This is a theory from a gravity-only simulation. But you go and you look out at the Milky Way and modulo this 18 ultra-faint satellites within 50 kiloparsecs, you find of order tens of satellite galaxies. So this leads people to ask where are the missing galactic satellites? And there's an obvious solution to this, of course. We say most of these halos, they're too small for us to see or they're too small to form stars at all. That has a pretty obvious corollary. According to abundance matching, that implies that the biggest subhalos should be hosting the brightest satellites. So this is how the missing satellites problem leads to too big to fail. So we can ask, does this actually work? And the answer, of course, since too big to fail is now about 5 years old, is no. If we take constraints on our satellites of the Milky Way, so here I'm plotting a constraint on their rotation velocity, which is proportional to the enclosed mass at their half-mass radius, half-light radius. Then we get points that sit down here in the plot, whereas if you plot the actual rotation curves from these satellites from a gravity-only simulation, then you find that they all live up here. So they all have too much mass near their centers to host the observed dwarf galaxies. Of course, there's an enormous caveat to this, right? Which is that these are gravity-only simulations. Right? So the obvious question is, can we solve problems like too big to fail just by adding known baryonic physics, or do we need to invoke unknown physics such as self-interacting dark matter or scalar field dark matter? So if you know me, you know that I also believe that we need to simulate the local group and not just an individual Milky Way. So rather than just pick out the Milky Way galaxy and its satellites here, I want to focus on the entire region of space that we live in, both the Milky Way and Andromeda. So that leads in to the first of our baryonic local group simulations with Fire 2. So here I'm just going to show you a couple movies. On the left is going to be gas colored by temperature. On the right is going to be star formation, or stars. This is going to be a false color SED, basically. And I want you to focus actually on this region of space. This is about where the local group analog is going to form. And I'll just let this run because it's very pretty. So a couple things that you can already see. One, it's a little hard to see with the lights as they are, but there's a lot of structure around here, a lot of sort of stars in the cosmic web. You can kind of see that we're forming nice disk galaxies here. I'll show you those better in just a moment. And you can even see a lot of the satellite galaxies orbiting around the central host in this image. So I'll skip the last because beyond redshift 1 is kind of boring. Here is our final 3D stellar density. Right, so you guys have probably seen images like this before. We have our hosts in the middle here. I basically set the saturation low enough that you can't really see any of the structure in the host. But let me remind you that these are very high resolution simulations, and there's a lot of detail in these. So if I zoom in on the central galaxies and show you those false color SED movies again, then here you can see that we're not just resolving this large scale volume, but we're really resolving the detailed structure of our hosts and our satellites, particularly the bigger ones. So you'll see that everything's kind of a mess until about redshift 1, then Romeo starts to form a nice disk. Juliet takes a bit longer. At about redshift 0.5, it's going to start forming something really very sort of wide, but not very tight. And we see this sort of diversity in general. Romeo, on the other hand, sort of chugs along after redshift 1. And then here, Juliet, you see, starts to get these really large spiral arms going way out to avoid her 30 to 40 kiloparsecs, actually. Okay, so moving beyond the central host, I want to talk about the satellites. Let's go back to this image. I'm sure that you guys have seen stuff like this before, but I love to do this, so I'm going to do it again. This is a 3D stellar density. I'm sorry. Very quickly, we've talked about fire before, but I'll just remind you, this is hydrodynamics, gas cooling, star formation, feedback from stellar radiation. Andrew went over all of this yesterday, stellar winds, supernova. In short, I would argue that these are the highest resolution simulations with the most physical prescriptions that have ever been run on these scales. Specifically, this simulation has a baryonic resolution of 3,500 solar masses. So our initial gas particle masses are 3,500. As to why this hasn't been done before, well, each run takes about 15 million CPU hours. So I ran 2 of these so far. That cost me about 30 million CPU hours, or about 2 years of allocations between DOE and NASA machines. So now the fade that I wanted to show you. This is our 3D stellar density. What does our dark matter look like? Wow, that's a lot of structure, right? So I'll show you that again. Here's dark matter, fade to stars, right? And most everything disappears. If you keep your eye on a couple objects, so for example, this one here, right? That's living in a pretty big halo. But there are plenty that you can see that completely disappear. So for example, this one here is basically not hosting any stars. So let's quantify this statement. How do we do in terms of the missing satellites problem? Here's our typical stellar mass function, number of satellites bigger than a given stellar mass. We can put Andromeda on the Milky Way on here. I'm just going to define satellites as everything within 300 kiloparsecs for the sake of ease, basically. And then let's go out and let's count up the satellites in our simulations. So Romeo and Juliet, the one I just showed you, lives here. This looks great, right? I would argue this is phenomenal. Similarly, I have Thelma and Louise. I told you I had 2 local group pairs. So our 4 hosts all do a really good job of sampling around the Milky Way stellar mass function. We don't have any LMCs, at least in these, but we know LMCs are rare and they're also very expensive to include in these simulations. Of course, Andrew told you guys, where is Andrew? Andrew told you guys about the latte simulations yesterday too. So that's now a set of 6 to 8 isolated Milky Way mass hosts. So I can go ahead and do the same game there. Plot all of those on here too, and you'll see that we again do a very good job of matching the Milky Way stellar mass function. However, all of these are underproducing the M31 stellar mass function. So you'll see on average it's about of order of 50% underestimate of the the M31 stellar mass function. That could indicate the M31 has a higher host mass than anything that we simulated. Our biggest host was about 1.5 by 10 to the 12. Or it could indicate that we need to have a later reionization in our simulations. In particular, most of our volume reionizes around redshift 10, as I recall, whereas we know now it should be closer to redshift 6. We're working on running some new simulations with that later reionization prescription, so I'll hopefully have some results for you in next year, I suppose. So the next question, of course, is are we able to solve the too big to fail central mass problem? So just to remind you, here's our too big to fail problem in a gravity-only simulation. In particular, this is Juliet, which is our classic Milky Way analog. You can see that in a gravity-only simulation, we have a lot of halos with too much central mass. So that's all these solid white lines here. Once you account for the LMC and SMC with these green lines, you can't really put any satellites in those dense, massive subhalos. However, when you add in baryonic physics, known non-exotic baryonic physics, then you reduce your central masses and end up solving the central mass too big to fail problem around the Milky Way at least. Okay? But we live in a local group and we have Andromeda as well, right? So let's look at Andromeda. So with Andromeda, in the gravity-only simulation, we find that the problem is not quite as bad. But generally speaking, we have a bunch of massive subhalos that don't have a known satellite analog. So there's nothing that we can put in these objects. There are just too many massive subhalos around our Andromeda analog. However, when we run with baryonic physics, then all of those lines shift down just like we'd expect, and we end up reproducing the M31 dwarf toroidals quite well. However, here I want to draw your attention to these. And these are basically dwarf elliptical galaxies. And you'll see that not a single one of our subhalos has enough central mass to host any of the M31's dwarf ellipticals, even at the 1 sigma lower bound error. And in fact, if I go and look in all of the 10 runs, the 10 halos that I just showed you stellar mass functions of, none of them are able to produce a single subhalo that's able to host one of these. So this is kind of the opposite of the central mass problem. This is a not enough central mass problem. And I want to emphasize this isn't just fire. If we go and we look in, for example, Nihao up here or Apostle over here, none of these are able to produce the dwarf ellipticals either. Right? So none of these simulations are able to produce a galaxy with a circular velocity bigger than about 30 kilometers per second at about 300 to 500 parsecs. So this might be a manifestation of the diversity problem in the local group, or it might be something different. I'm not sure yet. And you can kind of see that this is why this is so problematic. If we look at Ariano De Cintio's work, this is plotting the color indicates the central mass slope, whether you have a cusp in red or a core in purple. And you see that these galaxies live at a Voider 10 to the 8, which corresponds to a halo mass of 10 to the 5 to 10 to the 10.5 to 10 to the 11 or so, which is right where we expect core formation to be the most prevalent. So the dwarf elliptical scale, where we expect the strongest cores, actually have the densest stellar distributions, at least. And finally, I think I have 1 or 2 minutes left, so I'll just very quickly note that these are local group-like volumes, so let's leverage the fact that we have a local group and not just a Milky Way. So let's look at stellar mass functions in the local field. So what I've defined here is non-satellites beyond 300 kiloparsecs of either host, but within a megaparsec of one or the other host, basically for contamination purposes. And I would argue that there's some evidence that there are undetected galaxies in the local field below about 10 to the 5.5, 10 to the 6. But unfortunately, we need more simulations to really hammer that down, I think. So I'll just close with my conclusions. Elvis on Fire is in progress, but finally we're actually getting results. Suite of very high resolution simulations with Fire 2 targeting local group-like pairs. So we have resolutions better than 4,000 solar masses. We find no missing satellites or too big to fail problems when compared with the Milky Way satellites. We reproduce the Milky Way satellite distribution very well, I would argue. However, there's tension with the satellites of M31. It's not clear how you get high enough central masses to reproduce the dwarf ellipticals, and I think this is a problem that all simulation groups are probably facing. And we don't produce enough satellites in general, so that may be related to our host mass or our reionization. And these might be related. There's a chance that they're related, but I would argue that even if you make more galaxies, most of the work that we've done so far predicts that those big galaxies should be lower density than the smaller ones. And then finally, we predict of order 5 to 15 as of yet undetected dwarf galaxies in the local field, bigger than about 10 to the 5. LSST should find these, but we'd like to get more simulations to really hammer down that number. Okay, thank you guys.
Thank you. Questions? Yep.
So you said that you like to do local group, right? Is there any evidence so far, though, that there's different results coming from that?
So there was evidence from the dark matter only, right? When we ran dark matter only Elvis and did the careful mass matching of paired versus non-paired and measured the dark matter halo mass functions in the local field, we found that 80% offset. So more structure around local group like hosts once you go beyond their virial radius. This is not within the virial radius, that's right. We found identical results within the virial radius. So we're not seeing evidence of that yet, actually. I didn't make a big deal about that, but there's no evidence that the isolated fields are less rich than the paired fields. However, statistics are small, and this isn't a careful mass match sample in the same way that the original Elvis was. That said, there is another very preliminary work that I have started in the past month or so, looking at the star formation histories of these dwarf galaxies. And we are actually finding interesting differences between the local group and non-local group samples there.
More questions?
But that's very cool.
Abishai here.
I just want to reiterate the problem you pointed out, which I think is very interesting. No simulation that I know of can reproduce compact dwarfs. I think it's a big problem. We have a problem with not being able to produce compact dwarfs.
Yeah, I think
That's overall, we find it in our simulations, you find it there. It's a real open issue.
I agree. I think being able to reproduce both the dwarf ellipticals and the dwarf spheroidals, the full diversity of structure in the local group is going to be a really strong test moving forward.
Questions? No? Yes, on the back there. Can I give you?
Around the Milky Way. I didn't talk about it in the local field. It helps there, but I have. So it actually turns out that even if you assume cuspy profiles in our hydro simulations, which is not a good assumption in at least some cases, I haven't taken a close look at every single density profile, so I'm not positive what all of them look like, but a lot of them are chord. Even if you assume NFW profiles are to the -1, you still find no too big to fail problem. So what that says to me is that too big to fail is not solved, at least mostly, by transforming cusps into cores, but too big to fail is mostly solved by a combination of just removing mass from the subhalo overall, so that brings down Vmax, right? So you just lower the whole rotation curve, and destroying subhalos. I showed in a couple papers ago that when you add that central galaxy, that destroys a lot of subhalos, and Tyler was talking about that yesterday too. So it's a combination of destroying things, removing mass from them, and as far as I can tell, making the core is definitely second order. It helps, but it's not necessarily required.
I have a question. So M31 and then the Milky Way have quite different structural properties.
Yes.
So Milky Way has a small bulge, probably no classical bulge, pseudo. M31 has a big bulge. Do you get these differences in the simulation? Or?
That's a good question. So I haven't looked at the high-resolution simulations. I haven't looked at the structure of the central galaxies closely. What I'm finding for now, at least in Romeo and Juliet, they're both pretty disky. Neither of them has a strong bulge. But yeah, I would say the question of what do the central galaxies look like is better referred to Sarah, probably. I think she's been looking at that more.
So let's thank Cashin again.